So far we have seen a lot of deep architectures which relate to language and language learning. In the end of the course, I thought I'll touch upon other deep architectures that I would have ideally liked to present from scratch and show how it works for language. But this is a mini course and we have just 15 hours with us. So I thought I will club all these architectures together at the end, and so that when you have finished a deep learning course, you're aware that such things exist and how you can use them, and the general idea behind that, and how it has developed. Now, these architectures that I'll be explaining are equally applicable to both images and languages. And it is, as I said before, the idea that is important here. And we'll be seeing in the next three lectures, representation learning 1, 2, and 3, that how um, deep learning is used to generate vectorial representations that have some semantic value. So let's get started. Now, if you remember in the first class, we saw that deep learning itself is a representation learning exercise. We saw examples of representing numbers in Arabic numerals and in Roman numerals, and how the Indo Arabic numerals were far more uh, accessible for mathematical operations, and so on. Now, when deep learning is all around representation learning, why do we call a certain subset? The point to understand is that deep learning algorithm became popular in the 90s and 2000s, and a lot of parallel work was going on, but they didn't really click off, as we saw in the history section, until very recently. So a lot of different algorithms with different identities have been named uh, differently. So in this set of courses, by representation learning, we mean the simple task of converting your input into a vectorial representation, and that is somehow smart to model the task at hand. Now, this is not anything new. We have seen it in word embeddings. In RNNs and LSTMs also, there is a notion of representation. So in the next couple of lectures, we're looking at generic representations. And this particular lecture has some in unsupervised learning, and that is going to be the focus. Um, I hope you have covered supervised, semi-supervised, and unsupervised learning in machine learning course. But just a quick recap, it means I don't have any labels and I'm trying to extract as much information as possible from the data. So today we'll be seeing two major representation learning techniques, autoencoders and restricted Boltzmann machine. In the autoencoders, we'll be seeing two types, undercomplete and overcomplete, denoising and variants such as denoising, sparse, and variational. There are many autoencoders, but these are some of the popular ones that are out there. So let's get started with autoencoders. Now, as the name suggests, we are going to encode data on itself. That's why they're called autoencoders. And the idea is to get around the problem of dependent features. Now, whether it is word embeddings, whether you have actually done feature extraction, we will have a vectorial representation of the input, and those vectorial representations might have dependent features. You might have learned in your machine learning course that your data should be IID. Now, that is an assumption that is going to be far from true in the real world. What we do have as input to our deep learning network is, of course, data. And if data itself does not have independent features that are ideally distributed, then our algorithms do not have a guarantee to do the best they can. So how do we get this compact representation where we reduce the number of correlated features? That is the key idea of autoencoders. So it's also called self-supervised in the recent literatures, where you basically say if you don't have access to labels or annotation, it is known as self-supervised. Now, what the distinction I make between self-supervised and unsupervised is self-supervised does eventually lead to a supervised algorithm. It is a pre processing step, whereas an unsupervised technique has no access to labels whatsoever. What do I mean by that? So, if our task is sentence classification, for example, then self supervised um, is still applicable if we have trained our network separately to get embeddings, and those embeddings we are using further. So the getting the embeddings part is the self-supervised part, and the embeddings are then used for a downstream task. Now this became popular in the neural landscape. Unsupervised would be you have no labels whatsoever, and this is a distinction I am making. There is no consensus about these things, just these terms came across in different points in time. Now, let's get back to autoencoders. So, here, given a set of input vectors and there are no target outputs, we are simply trying to map the input back to itself. So, if this is my input x, I need to regenerate this x through this layer. And this is called the bottleneck layer. Now, how do we achieve this bottleneck? Popularly, it is through using fewer neurons. Or you can use the same number of neurons and have a sparsity constraint. That is, in every iteration, you turn off a few neurons, similar to dropout, which is the next point basically. So, this rather simple idea has created a lot of powerful literature in this space, and we'll see why that has happened. So, though this claims it's especially for images, I have used it extensively for text as well. So, the idea is from the input, you bring it to a latent space and then reconstruct. And we have seen ideas like this throughout this course, whether it is the singular value decomposition in LSA and so on, which is the next thing where we're going to compare with principal component analysis or SVD. So PCA or the principal component analysis, the idea is that you take a collection of vectors and produce a small set of vectors that can be used via linear combination. We saw how eigenvector analysis is used to do that, and it's very efficient for certain applications. For example, it is the bedrock of MP3 compression, which is why we have the Fourier and the wavelet compression. The power of neural network autoencoders, on the other hand, is the removal of linearity, and that we have seen it time and again, right from the first lecture on neural networks, how the activation function brings in nonlinearity. And we can use convolutional layers, we can bring about transfer learning. Transfer learning is basically you train for one task and then you use that network for another task. So, transfer learning, as you can imagine, is really hard because what it is originally trained for is not what it is intended for. So, with this set of ideas, let's move into how autoencoders work. So, principal component analysis of this data would have produced this single line, but an autoencoder would have produced this nonlinear projection. So, both of them produce a line, both of them produce a sort of dimensionality reduction, but the complexity of the line and the robustness of the dimensionality reduction is superior in an autoencoder. So the idea is we have an encoder and a decoder. It's quite similar to the sequence to sequence concept. And the only difference, of course, is that in sequence you had a sequence input and a sequence output. Here, of course, you just have your original input and your original output in some sense. But yeah, we use the word reconstructed output. So, though it is called self supervised, I think you can make out that it is actually a supervised algorithm, just that the input and the output are exactly the same. So, what this does is when we use less number of neurons, we are creating number one, a compression. So, the data is compressed and reconstructed. Number two, what we are doing is that we are creating a way to get rid of dependent features. So if I send in an input and it can be reconstructed with less features, obviously there are features here that are either redundant or a linear combination of them is powerful. And training is exactly like how we have been doing with neural networks, and it is just going to be your back propagation. Now, what are some of the issues we can have? Mm, it is extremely dependent on the data. The more data you have, the better it is. And because it is unsupervised or self-supervised, uh, if your input data is extremely noisy, it is not going to generalize well for the further tasks. Now, the second, of course, is that no matter how amazing your autoencoder has been designed and how clean your data is, we are doing a compression, so we are going to lose information. I'm sure you would have experienced when you get photos on WhatsApp, it's of far lower quality due to the compression, and the idea is very similar. Any form of compression is going to be detrimental to the original quality. So autoencoders are not powerful in themselves, in the sense they're not their task is not to perform compression but to form a compact representation that can be used. Now, we first did word embeddings. So, we saw that in word embeddings, we have language specific tasks for um, getting the embeddings, and they were not trained or they were not useful for the task they were designed, but the intermediate representation is powerful. Similarly, autoencoders are usually used for further processing or downstream processing. So here, because of these two features, autoencoders are usually used to train specialized instances of the algorithm. So what this means is that we use these autoencoder representations and then push it on to further processing for certain examples. So if you have uh, places where you have very few examples per class, for that particular class, we can use a representation. Next is, so I forgot to mention this task. I don't know if I have mentioned it in the lecture somewhere. So this is the MNIST data set where you have a set of handwritten digits and you want to recognize what number it represents. So once we reconstruct the output and we have a latent representation, this can then be used for classification. It is a labeled data set, so it has the image and the corresponding number. So we see here how it has the original input and the reconstructed output. Now in this slide, we're basically seeing the size of the intermediate latent autoencoder vector improves the quality. So if you have just 10, what you're doing is you have a huge space that you are compressing very fast to a smaller space. Now, also, since we have done convolutional neural networks, you can imagine that the encoder for an image can be a CNN. and it's of course completely up to the designer, but by default images use CNN. So any questions till now?
No, ma'am.
Okay, thank you.
No.
Okay, I'll move on. So autoencoders are of two types, undercomplete and overcomplete. Now, what do we mean by that? It just means that in the undercomplete autoencoder, the middle layer or the hidden layer where we are um, creating the bottleneck, the size is less than the input. In overcomplete, the middle layer is more than the input. Now, can you think of any issues if your intermediate layer is much larger than your input?
Duplicate values.
Exactly. You'll get duplicate values, and you can just copy the input and pass it on, right? So, if that is the case, then why are we going for overcomplete autoencoders, where we already have a neat structure of compression in the undercomplete and representation learning? So, because of duplication, we need to take care that copying doesn't happen. And if it has too many nodes, it is impossible to take a smaller input and then expand it too much and reconstruct. So, where we use this is we stack many layers where eventually we will have this bottleneck structure, like an hourglass structure. But it goes in a hierarchical fashion. So this has greater dimension than this. And the reason people explode over complete autoencoders is because the compression in undercomplete was causing a lot of loss in the information, and people realize there has to be a balance in the sense you need to have just enough number of nodes such that copying doesn't happen, but at the same time reconstruction is meaningful. So it is difficult to balance between both, and hence research was done on both undercomplete and overcomplete to explore how we can sort of balance both of these needs of an autoencoder. So this is how we came to the deep autoencoders. So what it does is, yes, we have an overcomplete layer, but it brings around a sort of compression and we reconstruct. So this is an image which is 28 cross 28, and you can imagine 28 cross 28 would be around some maybe 500, 600, that kind of input. And then we have overcomplete layers, but they are stacked hierarchically to provide a kind of compression. And this, of course, it's more complex and it requires more training. But if you have a large enough data set, you can imagine this brings in a lot more information, a lot more complexity, and a lot more depth to the network. We'll be seeing restricted Boltzmann machine later in the class, where the idea of using extra layers or hidden layers to explain things is explored mathematically. So this is where our overcomplete layers are used. They are very rarely used just as it is. Like very rarely I've seen 28 and then 1028 because of duplication, as you said, and so on. So this is how a typical autoencoder would look, that you have your CNN and then you have the CNN again. So in here is the reconstruction, and once you have that you can push it to the sigmoid variable. Now you can also take the intermediate representation, just take it out and put it in the sigmoid and classify. Now we come to sparse autoencoders. In the sparse autoencoders, what you do is that you randomly turn off nodes in every iteration. similar to dropout, and then you reconstruct. So this speeds up the training process and makes sure duplication doesn't happen, and it is more robust to noise. Now, this robustness to noise is what brings us to the idea of denoising autoencoders, which we'll be seeing here. Now, though autoencoders are powerful, because it is so sensitive to data and how we have modeled the data, this notion of bringing in robustness was introduced by denoising autoencoders. Now, the addition of noise in this case is not man made, it is generated by the computer itself. So, in this MNIST data set where you have 7 to these kind of numbers, we add a bit of noise in the sense uh, every pixel is going to have an RGB value, and you add plus some values, a fractional value, a random value, which follows usually noise is modeled using a Gaussian distribution. And this brings in some amount of gray in the picture. So this is not generated by a separate algorithm in your denoising autoencoder itself. It's just a one line code that will generate these perturbed images. So now your task is that your training set has doubled, one with the original data and one with this noisy data. And the output of this original data is the original data, and the output of this noisy data is once again the original data. So with this combination of both of them, we can get a far more robust representation for downstream processing. So we start with a clean image, we add the noise, we train our networks to get a decoded image. It's also like I said, that your training set essentially doubles. You have the clean image, you have the noisy image, but both of them, the output is the clean image. So, denoising autoencoders are very popular because they are scalable, they're robust, and so on. Now, we quickly look at variational autoencoders. Here, the idea is that your usual autoencoder has this network to perform compression, and compression is done on a linear level in the sense the representation is a weighted combination of your inputs, of course, followed by the activation function. So now, what is the drawback is that it's very very dependent, as we saw, on the data that you have seen, and it has no generalizability. So the idea is to bring in some more nonlinearity and some more learning, and you add Gaussian layers or continuous layers. So here it is discrete in the sense any of the autoencoders, the compression is here. Whereas if you have studied MP3 or JPEG compressions, they are kind of in the analog sort of domain. So, and what advantage that has is that it generalizes well in future. So if you have something that is discrete, for example, your compression is just say given an input and your compress is like 1034, it's very hard to generalize on unseen data. So here what we do is that we try and find out what is the distribution these intermediate representations are coming from. So instead of simply having path or intermediate representation, we now have to model distributions. I would have loved to take all these generative models together, but due to lack of time, I'm just going with the idea, which is that given X, I want to somehow model the probability of Z given X. And for the decoder given Z, I want to reconstruct X. And these two models are going to be probabilistic models. Actually, our word embeddings also, I don't know if I mentioned, they are probabilistic models. So it's not something new, it's just that it's more powerful than the previous autoencoders. So the encoder will take the input as the vector and it returns parameters for a probability density. Whatever it may be, you might have learned many probability distributions which have many features which are useful, not useful. So, one example is the Gaussian, which has a mean and covariance matrix. And then once you have this distribution, you sample from that and get the lower dimensional representation. And this is again passed to the decoder. Now you can imagine this is a far more complex network, and you need more data and more care in like back propagating and so on. Because here you're not simply back propagating weights, of course, eventually yes, but it should follow the rules of probability. So here again, the decoder takes the vector and returns the parameters. So here, the neural network parameters and this probability distribution parameters are learned. And this performs a good compression. So we saw that autoencoders generally have lossy compressions, but various autoencoders given enough data perform good compressions. Now, this whole discussion is because autoencoders for text are very popular. The only thing is, for images, we took CNN, and for text, we generally use LSTM, coupled with the deep embeddings that we have seen before in this course. So now we come to restricted Boltzmann machine, which is a sort of related representation learning task. So this is Boltzmann, an Austrian physicist, and we often take inspiration from many fields in the literature. So the idea is that it is similar to autoencoder. It's also a probabilistic model, which is why I introduced variational autoencoder a bit. And it's also called an explanation neural network because we're trying to explain why the data behaves a certain way. Now, restricted Boltzmann machine is a very fascinating network in the sense it is grounded in far more theory than many of these deep models we've seen. However, we will be looking at it from a very high level, and you can read up on it if you're interested. So, the key idea is that we have two types of neurons, visible and hidden, and they form a bipartite graph. By bipartite graph, I simply mean between layers, there are no connections among them and only between them. I'll be showing an image to explain this further. There is intuition similar to support vector machines. In support vector machine, complex data becomes simple in higher dimensions. So something that was quadratic in your current dimension, in higher dimension will become linear. Similarly, in restricted Boltzmann machine, what we say is that the visible data is explained by hidden factors. Now, this also comes in this notion of hidden factors, hidden nodes, also comes in Bayesian learning, which you might have seen in your machine learning course. So this is what I called as a bipartite graph. We have the visible units, we have the hidden units. There is no connection between the visible units and there are no connection between the hidden units. Once again, you have only the input. There is no notion of output. And what is the meaning of this? Here, what we are saying is that the visible units have no dependence between the vectors. So that's an assumption that the features are independent. So here is our input basically. And the hidden units are also independent. We are saying that these units have no, um, basically, the reasons that we are trying to discover have no correlation. Now, these are the causes for this data to behave a certain way. A nice example I saw yesterday was that if this is the input, say it's going to say how three people are coming to a particular place. Now, if there's a pattern that always these two people come together when this person is not there, we as a layman will think that's happening because these two sets of people don't like each other. But if you talk to them, they'll say that we are all strangers. There's no such correlation. But what if it's in a park and these two people come when a dog arrives because they like dogs, and this guy comes when a cat arrives because they like cat. So the hidden unit is the dog or the cat in this example. So what this implies is that the what our input initially is itself quite neat, in the sense these two will always come together and this is coming separately. But real world data, as you know, rarely follows such neat explainable data. Usually there's a lot of correlations that are there, but we don't understand why such correlations are happening. We might, of course, in an autoencoder, for example, get a complex sort of representation or reasoning for that. But these hidden units try to uncover that by adding another layer. So these are my reasons, and this is my visible layer. So here, what we're trying to do is that we have this notion of a energy model. So, what we want to see is how these hidden units explain why values in the input behave a certain way. As we see the input, we decide the weights and we learn an association between the weights. Now, the weighted sum of inputs that occur together have higher probabilities or score or lower energy. Why we need this concept of energy is because we don't have an output here. Even in an autoencoder, we did have an output. It was just that the output was the same as the input. So when you don't have an output, you cannot do backpropagation. So what do we do? So we develop this notion of energy between the visible and the hidden states, and say that if the input is on and the hidden state is on, then we take the weight between them. And we will also have a different notion for the positive and the negative weight, which is taken by the sign of the weight here. And we want to give a semantic that if it is a negative weight, then they don't occur together. And if it is a positive weight, they occur together. In the sense, the influence is positive if the number itself is positive, and negative if the number is negative. And we want to lower this energy. And this is now the gradient we are going to be reducing. So, um, 1 minute. Okay, I think I missed a slide. So basically, in backpropagation, we reduce along the gradient of the error. Here we are reducing along the gradient of energy. So how do we search across this gradient? In backpropagation, we just updated the weights based on the error, and we went along that gradient. Now here, there is no error. We have this notion of energy. So what we're going to do is randomly search among weights. In backpropagation, we added or subtracted the weights based on the error. Now here, there is no way to measure energy as such. And the weights here, we have more flexibility. You can change them randomly. And for that, we use this procedure known as simulated annealing. Annealing is a mechanical process where initially a metal is heated to a very high temperature and then it is cooled rapidly. So, what it does is it brings a uniformity in the structure. When the metal is hot, there's a lot of randomness, and it is cooled, there is rigidity, there is quality in the structure. We pick and use this process to search for a minimum. Now you can imagine just like how we had a neural network that you can just get stuck in a local minimum. What simulated annealing does is that it gives us a way to overcome this local minimum problem. So in backpropagation, we nudge the weights a bit to learn the correct weights. Here we do it based on a parameter known as temperature. Here I'll take the probability to be a function of both the energy and the temperature. Now temperature is a value you as a coder are setting, and you're going to reduce it rapidly from a very high value to a low value. Now what that is going to give us is dependent on this notion. So if my temperature is high, probability of changing the weight is 1. If the temperature is low, probability of changing the weight is 0. So what does that mean? So if my temperature is high, so let's say this is infinity, e power minus infinity is going to be 0 and my probability is 1. If temperature is low, let's say it's 0, then this becomes e power infinity, and then you have 1 by infinity, so it becomes like 0. So it's a function of lower energy otherwise. In the sense, if this is a reasonable number, we try to lower the energy as much as possible. So delta is going to be the change in energy. So what this basically means is we are searching for weights, we are randomly taking weights, and we will move towards the next weight only with this probability. And how do you code the probability as a developer? So let's say my current weight is 3, the next weight I'm going to see is 4, and the difference is energy is this. I compute this probability, say I get something like 0.7. Then I generate a number between 0 and 1. If it is less than 0.7, I change the weight. And if it is greater than 0.7, I don't change the weight. Now you can imagine, because we are taking it randomly, 0 to 0.7, you will have a lot of values that will cover that compared to the others. So you have a higher probability of changing the weight. So this is simulated annealing, which is the process we'll be using. And this is, I think, the only one we are seeing here where we will not use any form of backpropagation. So I found that quite interesting. Now the input and the weights with the hidden layers, just like our autoencoders, form the intermediate representation. In this lecture, I told that the weight, whether it's positive or negative, denotes that we have some kind of a positive or negative correlation with the hidden causes that we're trying to discover. And this is the idea we will be seeing in the next lecture for metric learning that I wanted to highlight here. So the two major representation learning networks we saw, they are not tuned for a particular task. They are, as I said before, used as pre-training for tasks. And they're often called self-supervised because they don't have labels and is closely related to unsupervised. It's just that unsupervised learning techniques came out a bit earlier, and they refer to things like clustering and so on. Here, however, we just call things as self-supervised. That's going to be later used perhaps for a supervised task. So here are some interesting applications. So if I give set of inputs and outputs as black and white image and color image, you can sort of get an interesting effect in the intermediate image. So you can imagine these two will have the exact same set of features, except the colors would be different. And that leads us to very interesting kind of tasks like these. And for text, you have so many applications. You can do spelling correction in a denoising autoencoder, for example, where your noise, unlike what I told before, which it was generated by text, it could be from a labeled data set which says this is noise, this is wrong spelling, and then you can remove the noise with the correct spelling. We can do topic modeling, where we don't know what are the topics that are there, But by examining the words that are generated by the hidden layer, we can find out where they belong. And so many. So to recap, autoencoders form a nonlinear compression. They have a wide variety of applications. Denoising autoencoders are more robust. Sparse autoencoders speed up computation. Variational autoencoders form a continuous version of these and are more generalizable. For restricted Boltzmann, I forgot to tell you why they are called restricted. So these things, this network is called a Boltzmann machine, and if we have connections between them, that is, if it's not a bipartite graph, then there is no restriction. Here we have the restriction, and that gives us an advantage that it's faster to compute. And the second thing is we try and find it independent causes so that we're not repeating information. So that's why it's called a restricted Boltzmann machine. So yes, we move towards minimum energy by contrasting positive and negative influences, and the hidden layers form a reduced representation. So thank you. Any questions?